Before the first stars shone, before matter had taken form, there was movement. Not the slow turning of a planet or the rotation of a galaxy, but something far more profound. The universe itself expanding, curling, twisting out of nothing into everything. In the instant after the Big Bang, motion became the first language of creation. Every rotation since, every orbit, every spin, can be traced to that original impulse, the first motion written into the fabric of space and time. Modern cosmology places the beginning of measurable existence at a moment known as the Planck time, 10 to the power of negative 43 seconds after the Big Bang. Beyond that boundary, physics as we understand it cannot yet see. The temperatures were so extreme and the energies so immense that the distinctions between matter, energy and geometry blurred into a single field of potentiality. What few hints remain of those early moments are preserved today as faint patterns in the cosmos, the cooling echo of a universe that was once condensed into a state of pure dynamism. When astronomers observe the cosmic microwave background, the residual radiation still saturating space, they are effectively looking back nearly 14 billion years to the afterglow of that first fire. Satellites such as NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck Observatory have mapped this faint light in exquisite detail. Though almost uniform, the background is marbled with minute variations, fluctuations in temperature no greater than 1 part in 100,000. These subtle ripples are not random. They are the fingerprints of motion at the universe's birth. Without them, matter would have remained evenly distributed. Gravity would have found no irregularities to amplify, and no galaxies or stars would ever have formed. Among these early irregularities, cosmologists discovered something unexpected: a slight alignment of the temperature fluctuations across vast regions of sky, a feature informally named the axis of evil. The term, chosen half humorously, describes an apparent large-scale directionality that standard cosmology struggles to explain. While most of the universe appears isotropic, identical in every direction, this faint alignment hints that the earliest expansion may have included a gentle rotation, a preferred axis imprinted during the first fraction of a second. Whether that alignment represents an artifact of measurement or the whisper of primordial spin remains an open question, yet its implications are profound. If the universe began with rotation, then every subsequent structure owes its shape, and perhaps its very existence, to that ancient turn. To imagine the mechanism that could produce such motion, physicists turn to the quantum world. Even in perfect emptiness, quantum fields are never still. They fluctuate spontaneously, creating brief pulses of energy known as virtual particles. When the universe burst into existence, these microscopic fluctuations were stretched by an event called cosmic inflation, a period of expansion so rapid that in less than 10 to the power of negative 32 seconds, the cosmos grew from subatomic size to macroscopic scale. Inflation, predicted in the 1980s by the physicist Alan Guth and later refined by others, transformed the residual trembling of quantum fields into vast ripples across space-time. Some of those ripples carried vorticity, a measure of rotational energy, converted directly from quantum jitter into the first cosmic spins. If this theory is correct, angular momentum was not added to the universe after its birth. It was built into the birth itself. Space did not merely expand, it swirled. Years of observation have provided indirect support for this idea. Variations in the polarization of the cosmic microwave background, known as B modes, record the imprint of primordial gravitational waves, subtle distortions of space produced when those early fluctuations twisted under inflation. Detecting such curls in light is akin to reading the fossil record of the universe's first rotation, frozen in the geometry of radiation. Once the expansion slowed and matter began to condense, these faint rotational seeds magnified under gravity. Clouds of hydrogen collapsed into denser knots, each fragment spinning faster as it shrank, conserving angular momentum. It is a simple and immutable law. In a closed system, rotation cannot vanish, only change its form. The same principle governs a skater accelerating her spin by drawing in her arms. When scale collapses, rotation intensifies. Out of countless such whirlpools of cooling gas arose the first stars and galaxies, the universe evolving not by chaos, but by a rhythm older than time. Every modern rotation tells part of that story. The Sun, a sphere of nuclear fire, turns once at its equator every 27 days. The planets, formed from the disk of dust encircling it, continue to spin with the angular fragments they inherited. Even now, 4.5 billion years later, the alignment of their orbits remembers that initial direction. Across cosmic distances, the Milky Way maintains its majestic spiral because innumerable stars obey the same conservation of movement. The pattern is universal. Angular momentum never dissipates, it merely redistributes, from the subatomic to the galactic. Observational evidence supports this continuity. In 2011, researchers at the Harvard-Smithsonian Center for Astrophysics analyzed thousands of spiral galaxies and discovered a slight statistical bias. More galaxies rotate in one direction than the other across particular regions of sky. The asymmetry is subtle but measurable, suggesting that the distribution of spin may be connected by a common origin. Newer surveys, building on data from the Sloan Digital Sky Survey and the Vera Rubin Observatory, continue to test whether this handedness extends across the observable horizon, an echo of the potential cosmic rotation hinted at in the background radiation. Even the dark, unseen matter composing most of the universe seems to share in this dynamism. Numerical simulations performed at NASA's Jet Propulsion Laboratory and Europe's Leibniz Institute for Astrophysics reveal that galactic dark matter halos twist and rotate slowly, guiding the luminous galaxies within as eddies guide leaves upon water. Without that enveloping rotation, gravitational stability would fail and galaxies would disintegrate. The invisible structure of the universe, therefore, is not static scaffolding, but an ocean of motion enduring since the first moment of time. Rotation is the consequence of broken symmetry, the physical expression of imperfection. The known laws of mechanics describe how movement behaves, but cannot fully explain its origin. The clue may rest in a concept called symmetry breaking. In the earliest instance after the Big Bang, all fundamental forces, gravity, electromagnetism, the weak and strong nuclear interactions, were united within a single perfect symmetry. In such a state, there is no preferred direction, no imbalance, and therefore no reason for anything to move. But as the universe expanded and cooled, that symmetry fractured. Distinctions between forces and particles emerged. With every slight imperfection, potential energy was released, forming gradients, differences that allowed change and motion. A universe of flawless balance would remain eternally still. The one we inhabit was born because balance failed. These theoretical perspectives find support in the behavior of matter on every scale. Subatomic particles such as electrons and neutrinos possess intrinsic spin, yet their handedness is not evenly divided. Neutrinos, for instance, always rotate with a left-handed orientation. Their mirror image counterparts, if they exist, remain unseen. This observed preference, known as parity violation, shows that nature itself distinguishes left from right, symmetry from asymmetry. It is a minute effect, yet it mirrors the same bias seen in the global structure of the cosmos. The laws that shape fundamental particles may therefore be the same that shaped the rotation of galaxies, a single principle expressed from the smallest magnitude to the greatest. In the present era, observation continues to refine these ideas. The James Webb Space Telescope, launched in 2021, has captured the light of galaxies formed barely 300 million years after the Big Bang. To astronomers' surprise, many of these ancient systems already exhibit organized rotation, spiral patterns in epochs once thought too early for such order. Their existence implies that angular momentum was embedded in matter almost immediately, long before the first stars completed their life cycles. The universe, it seems, did not acquire its tendency to turn. It was born turning. Some cosmologists have considered an even more radical proposition, that the entire space-time continuum itself possesses a minute overall rotation. If this is correct, then every object, every particle, every clock follows a trajectory on a subtly twisting manifold. Over billions of light years, that twist would accumulate, shaping the geometry of cosmic evolution. While current measurements restrict any such universal spin to extremely small magnitudes, even an infinitesimal rotation at the largest scale could seed the alignment observed in galaxy clusters today. The cosmos may be a vast gyroscope, its frame draped with the echo of its own beginning. Whether the universe truly spins as a whole is secondary to what the idea represents. It affirms that motion is not a transient property, but a condition of existence. From the inception of space and time, energy was never at rest. As expansion proceeds, that energy continues to evolve in new forms. The rotation of stars, the orbit of planets, the spin of atoms, the vibrations of light. Motion is the medium through which the universe remembers itself. When we trace this lineage back to its source, the question of agency often arises. Who or what initiated rotation? Physics answers with restraint. No external cause is required. Once the universe acquired even the smallest imbalance, conservation ensured perpetual motion thereafter. Momentum is self-sustaining. The first deviation from stillness was enough to set eternity in motion. The universe does not need to be wound like a clock because it is the clock, its energy eternally converting yet never extinguished. Thus, every turning planet is a relic of that original event. The faint curve of a galaxy's arm, the circling of oceans under the moon, and the spin of electrons within atoms all trace their ancestry to the same genesis of motion. To study rotation is therefore to read an unbroken chronicle stretching from the first microseconds of cosmic history to the present instant, the record of how everything came to move and why nothing can stop. The evidence will continue to accumulate, measured in background polarization, galactic alignment, and gravitational waves. Each discovery refines a single truth. The cosmos did not emerge from rest into motion. It emerged as motion. Creation was not an explosion, but a turning, an unfolding spiral that endures in every orbit and every rotation yet to come. Motion, once begun, has never ended. It is the continuity connecting the birth of matter to the turning of minds that perceive it. We, standing upon a spinning world, feel none of the velocity that sustains us. But through instrument, observation, and thought, we can sense the deeper rhythm, the echo of the first motion, still carrying every star, every atom, and every human moment through the boundless expanse of time.